All right, hello. My name is Brad Orr. I'm chair of the physics department, and it is really a great pleasure to welcome you to the 15th annual Ford Distinguished Lecture. First, I'd like to take a moment and thank the Ford Motor Company for their very generous support of the physics department and the University of Michigan. They have been one of the largest contributors to the University of Michigan, and I want to thank them for endowing this in 1999 and allowing us each year to bring in an international speaker to meet with our faculty and students. Andrea spent a lot of the day talking with students, and it's been very enjoyable for them, I'm certain, and certainly enjoyable for all the faculty members who've been able to talk with you today as well. So thank you to Ford. We have some visitors from Ford today. We have Dr. Jim McBride, who is the Senior Technical Leader, Autonomous Vehicles Research and Advanced Engineering. He is a physics U of M alum, and his advisor is Roberto Merlin, and they are both in the audience. Can you just raise your hand? I'll have you stand up in a moment. All right, so we have deep connections to Ford. Here's number one. Number two is Dr. Bita Gathari, a technical expert in materials manufacturing department, research and advanced engineering. She is also a U of M physics alum. So again, Ford is benefiting from our physics department education. Lastly, we have Dr. Shuzu Huang, who is the Director of Analytics R&D Global Technology Leader in Ford Global Data Analysis, or Analytics and Analysis. Now, he did not get his degree at the University of Michigan Physics Department, but he is married to a University of Michigan physics professor, so he too is connected to our department. If I could have you three stand up, please, and a round of applause. Now, I know often there are many other Ford employees who come, former Ford employees, current employees from Ford. I'd like all of you to stand up now, and we could acknowledge all the former employees. I know we also have Craig Davis here, a former member of the research division. Where's Craig? Craig. You can stand up, you can lead the way. But there must be others. There are others in the audience. Please stand up. So thankful for the Ford Motor Company for allowing this lecture to take place. So today, unlike some other days where I just do it off the cuff, I actually did some research. In 2003, Ford Motor Company Chairman William Clay Ford Jr. commented that the automobile industry was about to experience the most profound and revolutionary changes it has seen since the Model T first hit the streets. So what was he talking about in 2003? So I think the things he was talking about there were petroleum-based cars moving towards electric-based cars. And so we've seen a lot of progression in the last decade and a half on that. We heard last week a talk from Stirag Uher on thermal electrics and how thermal electrics are going to be able to collect waste heat from the internal combustion engine or from any engine and turn that into electrical power inside the automobile. So another advance made by materials. I'm sure you might be working on that. But something he didn't talk about at that time was the digital revolution and the idea that cars could talk to one another and potentially avoid accidents because someone's coming around the blind corner and the cars talk to one another. I learned something just out at Coffee Cookie Hour that technology, which was purported to be able to save or prevent 80% of automobile accidents, is already now obsolete. It hasn't been implemented, and it's already obsolete because it's being replaced by autonomous cars that don't have to talk to the car around the blind corner, but just can handle it when the car appears. And so autonomous cars, which are racing forward, are just going to revolutionize the automobile industry. So a more current quote is that in 2016, Mark Fields, the current CEO of Ford, said, "We are on the cusp of a mobility revolution." He said that Ford will have autonomous cars on the road in partnership with ride-sharing in 2021. That is not so far away. All right? So I think it is just an unbelievable advance that we've had since this lectureship has been endowed in the automobile industry. Similarly, the revolution in what has gone on in cosmology, astronomy, astrophysics has been equally amazing. When I started out as a graduate student, we thought we understood the universe. And every year after that, we know that we know less and less and less and less. And so today's speaker is riding the cusp of this, inventing new technology, just like the automobile industry is inventing new technology, and learning more and more that we don't know about the universe. So I'm really looking forward to today's talk to learn about more things that I don't know. And to introduce our speaker, we have Professor Fred Adams.
Hello, everybody, and it gives me great pleasure today to welcome today's speaker, Professor Andrea Ghez from UCLA. She is the Lauren B. Leichtman and Arthur E. Levine Chair in Astrophysics at UCLA. Let me just tell you a little bit about her history. She was born in New York City a few years ago and grew up in the other large city of Chicago. She then went back east to go to college at MIT, and then went back west to get her PhD at Caltech. She then did a postdoc at the University of Arizona where she was a Hubble Fellow. Back in those days, they only gave out a couple such Hubble Fellows per year, so that was even more prestigious then than it is now, and it's still quite a big honor. So after her postdoc, she went back to LA and became a professor at the University of California, Los Angeles, and she's been there ever since 1994. So along the way, Professor Ghez has accumulated an extremely large number of awards. So in the interest of allowing her to actually give her talk, I'm just going to give you a few highlights, where these highlights include the Sackler Prize, the Crawford Prize, a MacArthur Fellowship, and she's a member of the National Academy of Sciences. So in her early work, just very briefly, Andrea focused on studies of star formation and young stellar objects and young stars, especially their binarity. She studied binary stars, binary fractions, and how they evolve in the early phases of the star formation problem. Those same techniques that she was using and developing further allow you to do a number of other problems. So in the 90s, she transitions to studying the galactic center, and that's the topic of her lecture today. So without further ado, let's welcome Andrea, who's going to tell us about the monster at the center of the galaxy.
Thank you. It's a pleasure to be here and to have the opportunity to interact with students and faculty studying a host of different things. I find I always learn a tremendous amount in visits like this. So I'm an astrophysicist, and in astrophysics we get to ask some of the biggest questions. We get to look at problems like the beginning of the universe, the origin of life, and black holes. And black holes are the thing that I'm most fascinated with. And I have been, as Professor Adams mentioned, at UCLA for quite some time. And the reason UCLA was so interesting to me was the technology. So it's a really nice connection to this lectureship, because everything I'm going to talk to you about today is really technology-driven discovery. So as an astrophysicist wanting to study the universe, having the biggest telescope in the world is really key. It gives you the technology that gains you access. And as I'll share with you, the Keck telescopes are the largest telescopes in the world. They're co-owned by the University of California and Caltech. So having a job at one of these institutions for me was just a dream job. I can remember the place I was when I read the job ad for UCLA, so, thinking this is the job I want. So I feel very privileged. And UCLA in particular focused on new technology. In other words, they recognized that there was an area of technology development that was about to explode as these telescopes went online. That's the area of infrared astronomy, an area in which, of course, aerospace industry is driven by, so that's in Los Angeles. So UCLA invested very heavily in this arena. So within this collaboration between UC and Caltech, UCLA takes charge or advances the forefront of infrared instrumentation. And I'm an infrared astronomer, so that's really why it's such a great match. And I was interested in using these telescopes in a very new and different way, which I'll get to. So a lot of my work is really driven by the desire to develop new methods and new technologies in order to make scientific discovery. So my group is really divided into three things. Science, in other words, using high-resolution imaging, the ability to see fine detail. I'll go into this more in detail. To do black hole science, to advance the technology that allows us to do that science, and of course, education and public outreach. Now, I'm going to start with a question, which is, how do you observe something you can't see? And that is an essential question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape it, not even light. So we can't see them directly. So the story I'd like to tell you today is how we've been able to find a supermassive black hole, and I'll get to what that means in a moment, at the center of our galaxy. And this has proven, given us the best evidence to date that these exotic objects exist in the universe. But it's also given us a great opportunity to explore the exotic physics associated with these unusual objects, as well as to understand the astrophysics of these objects in terms of the role that they play in the formation and evolution of galaxies. Now, to begin with, it would be helpful if we all agreed on what a black hole is. Now, while it does require relatively exotic physics to properly explain a black hole, the way I would like you to think about a black hole, which is actually the way I like to conceptualize them, is that they're objects whose mass is confined to zero volume. So if you think about density, which is mass divided by volume, density goes to infinity. And in physics, anytime we have a quantity going to infinity, it's known as a singularity, which is like a giant red arrow that says, you do not have your description of the physical world quite right here. Okay. So, and in fact, any object can become a black hole. I just have to figure out how to make it infinitesimally small. So this big red arrow, in terms of physics, means that, or represents, that we do not know how to make the study of general relativity, which is the study of things with very strong gravity, work together with the study of quantum mechanics, which is the study of very small things. And of course, black holes represent both. So presumably, when we figure out how to make these two fields come together, we will be able to provide a proper description of what a black hole is. But in the meantime, we can ignore that small little detail that we actually don't know what they are, but we can find them and we can study them. And in order to find them, it's useful to recognize that while this object itself is infinitesimally small, there is a finite size I can associate with the object. It's an abstract size. It's known as the Schwarzschild radius. It's also known by its popular name, the event horizon, which was popularized by Star Trek. It's the point of no return. And it's useful from a number of different perspectives in terms of conceptualizing what a black hole is. Every object in the universe has a Schwarzschild radius associated with it. And it's the radius at which, if that object was confined down to that scale, it would be forced to become a black hole. In other words, at that point, gravity would overcome all other known forces, and the object, due to the force of gravity, would be forced to become the infinitesimally small object. Okay, now, so that means that you could become a black hole, your cell phone could become a black hole, or any other object you'd like to turn into a black hole, in principle, could turn into a black hole. But you'd have to be able to scale it down to that size. So let's look at the different objects that we might turn into black holes. So let's start with the Earth. If we could take the Earth and put it in a giant compressor and scale it down to the size of a sugar cube, it would be forced to become a black hole. Somebody recently pointed out that young people probably don't know what a sugar cube is, so it's like a penny. Now, the more massive the object, the bigger the Schwarzschild radius, and it scales linearly. So you double the mass, you double the Schwarzschild radius. So if I could put the sun and compress it down to a university's campus. I put UCLA here. I'm a little biased. Should have put University of Michigan there. It would be forced to become the Schwarzschild radius. Black hole. Now, all right, so now we have what a black hole is, and the essence of what one needs to do in order to prove that black holes exist, which is you need to show that there's some amount of mass that's confined, ideally, to within its Schwarzschild radius. That would be the ultimate proof. Now let's look at where black holes might turn up. And in astrophysics, there are two groups. And here, actually, you see very clearly two different modes by which science proceeds. So there are the ordinary mass black holes, as if there could be anything approaching ordinary about black holes. But these are the ones that were predicted by theory. In other words, when people thought about the evolution or ultimate fate of very massive stars that are more massive than roughly 30 times the mass of the sun, it was recognized that at the end of these stars' lives, the outer parts of the star would explode and be shot off into the universe. So this is a very beautiful picture of that process. This is known as a supernova remnant. But in the inner parts of the star, it was pointed out just from theoretical calculations, just following through with what we know about physics, that the inner part would collapse to become a black hole of roughly 10 times the mass of the sun. So the notion of black holes started here with the ordinary mass black holes. And massive stars, we see massive stars all throughout our galaxy. So in fact, we expect that our universe and our galaxy should be pervaded by these stellar mass black holes. Now, and in fact, we have great observational evidence for this. We used to be good, and it got even better with the detection of LIGO of two stellar mass black holes merging. Now, the black holes that I'd like to focus on today are the supermassive black holes. And these are the ones that are, as you might imagine, really more massive. They're 1 million to 1 billion times the mass of the sun. And they were not predicted from theory, but rather the origin of the idea of supermassive black holes came from observations. And the observations suggested that perhaps supermassive black holes reside at the heart of galaxies. Now, this is a picture that's taken on a very different scale from the one that we were looking in the previous slide. So the previous slide was looking at one star. And every object that you see in this picture is a galaxy, except for one star in our own galaxy. So you can see that galaxies come in all sorts of shapes and sizes. Let's focus on maybe the one on the top left here that looks like a spiral. That's, as I'll say, kind of what our galaxy would look like. And that galaxy has 100 billion stars, so a very different scale. And we think that perhaps there's a supermassive black hole at the center. Now, what we see here is the light from stars. We're looking at a picture that's taken in the optical, which is what your eye responds to. So you might ask, why did people think about the supermassive black holes? And it came from a small set of galaxies. They're known as active galactic nuclei. And they're about 10% of the galaxy world. I like to call them prima donnas. They're the prima donnas of the galaxy world because they're kind of show-offs. And this is a picture of one. And this is a picture in the at radio wavelengths. And the galaxy is contained in the center. So if we look in the center here, right here, this is where all the stars reside. But what you see instead of the starlight is you see jets emanating out from the center, and we can measure how fast these jets are moving. So you can easily tell that there's a tremendous amount of energy in the jets that are coming out of the center. It's also true that if you look at the center, there is a little bit of light, or quite a bit of light actually, if you compare it to starlight emanating out of this region, but it has characteristics that do not look like starlight at all. So from these observations, people said, well, maybe we could explain this by the presence of a supermassive black hole. A supermassive black hole that is feasting on a tremendous amount of material just outside its event horizon. So you can think of these supermassive black holes as black holes that are dining, like having a Thanksgiving feast. And that material is not only falling through the event horizon and very hot, which is why we see it, but also driving these jets. That notion that black holes reside at the center of these special class of galaxies led to the suggestion roughly 40 years ago that perhaps all galaxies harbor supermassive black holes at their centers, but they're just stealth black holes. Or you could also say black holes on a diet. There's nothing around them that's lighting them up because they themselves do not shine. And this is a galaxy. This is a zoom into the galaxy that we were looking at the top left. And as I said a moment ago, it's a spiral galaxy, flattened disk-like structure, very much like what our galaxy would look like if we could get outside of it and look back. And our sun is about halfway out. And you might notice that there's an intense concentration of light as you go to the middle. So everything gets more exciting as you go to the center of galaxies. And we live out in the suburbs where things are nice and calm. So if we want to ask this question about the presence of supermassive black holes in all galaxy, and furthermore, to prove that these supermassive black holes really do exist, our galaxy is simply the best place to look because it's the closest center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away, so our galaxy center provides a great laboratory for doing this kind of work. This is a picture that's taken on Mauna Kea in Hawaii, and you see the plane of our galaxy. So you see the fact that we live in this flattened disk-like structure, and we're looking out, and you see that concentration of white light, which is the concentration of starlight. You also might notice the band of a lack of light. And that lack of light comes from all the dust that exists in our galaxy. There's not only stars and gas, but a lot of dust. Now, I'm from Los Angeles. I have a very good appreciation for what dust in the air does. Turns out the particle size of the dust in our galaxy is just like the particle size of dust in a smoggy city. And it's a very effective blocker of optical wavelengths. The way you can understand this is dust is very good at blocking light that has a wavelength that is comparable or smaller than the size of the dust particle. So if you start to observe light that has a wavelength that's longer than your dust particle, it can actually make it to you. So you can see here why the realm of optical astronomy and astrophysics doesn't allow you to see the center of the galaxy. You just can't see it. It's obscene. 1 out of every 10 billion photons that are emitted from the center of the galaxy makes it to us. We can't see it. But if you go to the infrared, and in particular 2 microns, which is where I've done most of my work, 1 out of every 10 photons or light packets makes it to us. So you can see the center of our galaxy. So hence you see the attraction to infrared astronomy. Now, if we want to prove that there is a black hole, the best way to do this is to watch how stars move. You treat the stars like little test particles that we talk about so often in introductory physics problems. That's what these stars are from my point of view. They're just little test particles that are going around. And they're feeling the force or the gravitational force of the black hole, if it's there. And they orbit in this way for the same reason that the planets orbit the sun. It's due to the pull of gravity. And by measuring the rate at which those objects go around and the size of its orbit, I can figure out the mass. And the scale of the orbit tells me how the size of the region that I've confined the mass to. If you hark back to the beginning of the lecture, that to prove that there's a black hole, I need to show that there's a lot of mass inside a small volume. And because my goal is small volume, this means that I want to see the stars that are as close to the center of the galaxy as possible, which tells you why I am very obsessed with working with very large telescopes. So there are two campaign promises of big telescopes. The first is that a very large telescope can collect a lot of faint light, can collect very faint light. It's like a light bucket. So the larger your mirror, the more light, like rain, it collects. So if you want to study things that are very faint, like you want to understand the origin of the universe, you want a big light bucket. That's why you care about big telescopes. But from my perspective, I care about the second campaign promise, which is the larger your telescope, the finer the detail you should be able to see. This is the characteristic of angular resolution. The analogy I like to make for that is if you were to go to see the art form that uses pointillism, which uses dots, the closer you get, you start to be able to resolve those dots. So that's what large telescopes allows you to do, is actually to see that detail. Now the Keck telescopes, there are two of them, we're very fortunate, each have a diameter of 10 meters. And to give you a sense of 10 meters, that's like the width of a tennis court. And the design of these telescopes was really innovative. This was, in fact, at the time that these telescopes were built, people were saying, it can't be done. Because people had always used monolithic mirrors, and this telescope is made up of hexagonal segments. So, and actually, after this telescope was built, most future large telescopes have used this architecture. So an example of that would be James Webb Space Telescope, which is about to be launched. So actually, I'll go ahead and ask you this question. Where would you put such a telescope? I've probably already told you that, but. Well, up above the atmosphere would be great. Turns out today we don't know how to launch a 10-meter class telescope. So if I'm stuck with the ground, where would I put it? The highest. I want height. I want altitude. I want to get above as much of this atmosphere as possible. Hawaiian Islands would be a good place. So why Hawaii? Hawaii is where these telescopes are. So why is Hawaii such a great place? So it's got the height. It's up at 14,000 feet. Which is an interesting place to have to work because it turns out your brain does not work very effectively, and up at 14,000 feet. So there are lots of great stories about how ineffective scientists can be up at 14,000 feet. So when I first started this work, we actually physically had to go to the mountain. This is one of the aspects where the technology has just changed radically over the course of the experiment. So we would go up to the top. My very first debate with my grad student up there was what was 128 divided by 2. We could not, you're trying to do your best work. This is not the condition. And again, to maybe give you another perspective of this is precious telescope time. It operates, these facilities, the construction cost was $180 million, and each night is operated at a cost of roughly, or valued at $100K per night. That's $1 a second. You do not want to be having debates about what 128 divided by 2 is when you're using this telescope. The typical UC astronomer gets 2 nights, roughly 2 nights in a year. So this is precious time. So in fact, they've gotten astronomers off the mountain for obvious reasons. You can now control the telescopes from Waimea, which is where the headquarters are. And that began in 1998. And then roughly 10 years ago, it became possible to control these telescopes from campus. I mean, this is not surprising in terms of how technology has evolved, but it has really affected, as technology is, there are pluses and minuses to each place in which we have observed over the last years. The greatest things about being able to observe from campus is, of course, that we can much more easily involve our students. You do not fly a class of students out to Hawaii to just show them how it works, especially if it's your precious time. But you might allow them to join you for an hour just to see how it works when they're at UCLA. Okay, so that's the height. We love height, okay? Hawaii is a volcano. There's 5 of them. And there are some that are active and some that are dormant. Mauna Kea is a dormant, so according to the geologist, it will not explode for another 1,000,000 years. I'm married to one, so I have to trust them. Now, what are the other advantages to being in Hawaii? Light pollution. Okay, yeah, we are creatures of the night. We have built this large telescope to collect the faintest things. We do not like light. What else? And here's a picture to go with that statement. This is I love this picture. This is a montage of the world at night, and it shows you an interesting tension within the field of astronomy and astrophysics, which is, here you are, you're developing the most advanced tools in your field. This is cutting edge. There's all sorts of technical hurdles that have to be developed for these forefront facilities. And you want a dark sky. So that usually puts you in opposition with access to where technology is being developed. So you can see you might want to put it in the middle of Africa, but of course you would have difficulty in terms of your access to advanced technology. So Hawaii is actually one of the few places where it's a dark sky, and there's lots of local ordinances to keep the sky dark. So if you've ever been to Hawaii, you'll notice the lights are yellow. That's because they're emitting in a small wavelength regime, so that can be easily notched out. And they're all covered so that the light is only shining down and not up. So astronomy is one of the few Hawaii is one of the few places where astronomy is actually an impact on the economy. It's the #2 economy on the island of Hawaii. So there aren't too many places where astronomy can have that kind of impact. You might guess what #1 is. Tourism. Okay, so we don't let the hotels do laser light shows. But there's going to be irony in that in a moment. Okay, so we've got dark skies. What else do we have? Hawaii. Lack of smog. We don't like smog. And there is another thing that we do, so we like clear air, and we also like calm air. So we want to be as high up as possible to get as little air to deal with. But if we have to put up with it, you want the airflow as smooth as possible. You want a laminar flow. And it turns out being by a big body of water helps you. So if you look at where all the premier telescopes, the biggest telescopes in the world are, they're always next to a big body of water on a mountain. So ideally, it would be an island from the calm perspective. So Hawaii has that going for it. It's high and surrounded by calm water. Okay, so there's very little atmosphere. However, the atmosphere is an enormous headache if you want to get to the business of getting to the second campaign promise, which is your ability to see fine detail or high angular resolution. So we love the atmosphere. It allows us to survive here on Earth. But for astrophysicists, it is a pain in the rear. So, and so I've spent a lot of time and energy thinking about how do we overcome this debilitating or potentially debilitating effect of the Earth's atmosphere. So you can think of the problem of the Earth's atmosphere as like looking at a pebble at the bottom of a stream. You know that if the stream is moving past you, it's very hard to see the pebble. So what you really want to do is make that stream still. This is some data that we took very early on in our work on the center of the galaxy. And if there were no atmosphere, you'd be looking at 5 bright stars there, and they would be rock steady. And each star would be the size of the smallest structure that you're seeing dancing around. I mean, I think of this as a bunch of bug splat patterns that are happening. And this is because the light, which has been traveling to us from the center of the galaxy, and this is, to me, another kind of profound statement. It's been traveling to us for 26,000 years. And in the last 30 microseconds, it hits the top of the atmosphere and gets completely messed up. They say accidents happen close to home, and that is definitely the case here as well. So the other analogy one might make, which is useful in terms of understanding how we correct for this, is that it's like the atmosphere is like a circus funhouse mirror that distorts you. And what we want to do is we want to figure out how to put in a second circus funhouse mirror that makes you flat again. Okay. Now, obviously, as somebody pointed out, the best thing to do in terms of solving this problem is to go to space. So that definitely works. That is the solution of Hubble Space Telescope. You get above it. It's also the solution of James Webb Space Telescope. But it turns out these telescopes are still smaller than what we have on the ground. So we said the Keck telescope is 10 meters. Hubble Space Telescope, which is already up there, is a 2.4 meter telescope. Now, the scientific benefit or the science return goes for me as roughly the diameter of your telescope to the 4th power. Now, because I'm not at the sum of Mauna Kea, I can actually do this math. That's a factor of 4, and so it's 4 times 4 times 4 times 4. That's more than a factor of 100. Now, think about anything in your life that you'd like to extract at least a factor of 100 times more. That is the benefit of figuring out going more. And that's just from your being able to take a picture. And as I'll comment on a moment, we get even further factors. We get up actually all the way to a factor of 10 million by the end of this work. So the first step on our progression is just you want to beat the atmosphere. So we've used a variety of technology. And again, this is a part of the story where the technology has just exploded from the beginning of the scientific this project to the end. So we can take, well, this gives you a sense of it. This is a technique called adaptive optics, which corrects for the atmosphere with hardware. And you can see in the center of this box, which is where I think the black hole is, you see much better with this technology than without. And just to give you a little bit of sense of technology, since this is the Ford technology, let me show you some things that I wouldn't generally show in a public talk. So in the beginning, what we did is we took all those short exposures and we brought them back and we computationally solved for what was underneath this. And nobody had done this, so it was the best technique out there. And I have to say, I really love looking at this animation on the right. Actually, let me show you better. So this is real data. This is not souped up data. This is just one picture every year, and it shows you how the stars move. Oh, and I wanted to comment for the students in the room. When we first proposed this work to the Keck telescope, I was a brand new assistant professor. I thought I had a great idea, and I had built this little widget to collect this kind of data. The time allocation committee, which is in charge of the telescope resources, said no. Not only will your technology not work, but you won't see anything, and we really don't think there's going to be a black hole there for all sorts of other reasons that they could provide. So this gives me great pleasure to watch. But I had very wonderful colleagues at UCLA who lent me their telescope time. And as I mentioned a moment ago, this is a pretty precious resource to just show that this technique of being able to work in software, so to extract this, worked very well. And again, for the sake of the students, we've had to build all the tools. This is not a technique or approach that had been used before. So when we went to the telescope the first year, it took us a year to analyze the data. The next year, it took us a month. The year after, a week. And now we can do it at the telescope. So some of this, you have to make big long-term investments sometimes for a high return. Okay. So you can probably see my favorite star in the universe happily zipping around. Okay, but technology, that wasn't the end of the story by any means. In fact, I had no idea what was coming in terms, well, I did have some idea of what was coming. I just didn't know how powerful it would become. So it turns out that astronomers and astrophysicists are not the only people who care about looking through the atmosphere. There are other people who like to look up and down, and that's the military. And of course, the military has far more money than the astrophysicists do, and had gotten pretty far. So as our community started to advance the technology, at one point they said, we know how to do a lot of this, and declassified this. This happened in the early 90s. So there was this huge push forward at that point because there was a declassified technology. And then the job was just to figure out how to take that application, which was really near field, and make it work in the far field. Okay, so I've talked through some of this. This shows this technology, and there are a couple miracles that happen, like the telescope dome going through away, and you see the light coming through the telescope. So it's bounced off the primary mirror, and now is going back into the instrument bay. And we're going to look at the adaptive optic system. So far, we've seen the light come through as a path, and in a moment, instead of a path, we're going to look at what's known as the wavefronts of the light. And if there were no atmosphere, these wavefronts would look like flat pancakes. So here comes the light travel direction, and just bouncing off the magic mirror. It's called a deformable mirror, and this is the mirror that's going to try to take the opposite shape of what the atmosphere has imposed. So now it's not working, so you see the bug splat patterns. And now I think we're going to see the affected wavefront. So instead of looking like pancakes, they look like Pringles potato chips. And they look corrugated and have different shapes all the time because the atmosphere, like a stream of water, is moving all the time. Now we close the system, and we take this deformable mirror, and we feed back the information of how to take the correct shape so you undo what the atmosphere is doing, and you get pancakes coming off of it. And when you feed this into your detector, it's going to look sharp again. And for the first time in my professional life, I'm taking a science exposure that's longer than 1/10 of a second, which means there's a lot more that we can do. Okay, this is so much more powerful, and even though it's so much more powerful, we're still only in the early days of this. Just to give you a little bit of a sense, on the left is the early days that we were looking at. To me, this is like those old-fashioned black and white movies that were taken of your childhood. They were the best thing at the time, and you look at them, they're kind of cute and yeah. But that data is incredibly precious to us. And on the right is what we can do today. Oh, it's a factor of 10 in almost any way we can measure it in terms of corrections. You can see stars that are a factor of 10 fainter. You can position those stars a factor of 10 better. And in terms of this game of measuring orbits, that is essential. Now, to get this technology to work, in other words, to know the shape of your deformable mirror, you need to do something. And so, in fact, we do something kind of ironic. Remember, we don't let the hotels do laser light shows. We shine 2 lasers up into the atmosphere. And the way this works is that, well, it's kind of like 2 giant laser pointers in a sense. You see where the center of the galaxy is. But it's not that light that's useful to us, actually. That's just dust scattering the laser light. So what that laser is doing is it's tuned to a transition in the sodium atom. And it turns out that meteorites, through meteor showers, come down. And there's a very thin layer of sodium atoms that's trapped up at 90 kilometers. And a very, very thin layer. It's just chance. It's good fortune for us, because then we can take this laser and stimulate those atoms to shine, and then watch how those atoms that light comes back to our telescope. And that's the light that we use to correct the atmosphere and do this business. So these are called artificial laser guide stars for obvious reasons. And this is a night that we were actually studying the center of the galaxy with both Keck telescopes. I felt like the Queen of Mauna Kea that night. It was just an enormous privilege. Okay, so we've been doing this now for roughly 23 years. I mean, it's hard to believe. If you had told me this at the outset, I would not have believed you that we would still be doing this. And this is because it just has gotten better and better. So the beginning was you just wanted to see them move. Remember, people said you won't see anything, that you're going to be rock solid, even if you can take a picture. They've not only not moved, but they've made complete orbits. So there you see my favorite star. It's gone all the way around. It has an orbital period of 16 years, which means it's the best probe of your potential. So it's the one that has told us what's at the center of the galaxy, and it's the one to watch, actually, because it's about to make its next closest approach, which means the effects of gravity, and in particular general relativity, are strongest there. So that's kind of our future. But historically, that star tells us that, well, taking a step back, before we started this work, just from the average motions, they weren't along the line of sight, which is a different technique. You could tell that there was 4 million times the mass of the sun inside this big circle. And you can see there's a lot of stars, gas, and dust. So you couldn't claim that there was a black hole there because you were so far out from the Schwarzschild radius. Now, this ability to measure orbits, and this is the only place in the universe you can measure orbits at the center of a galaxy, has confined that mass to a region that's 10 million times smaller. In other words, you've advanced the case for the existence of supermassive black holes by a factor of 10 million. And that's a huge step forward. And at that point, we've actually run out of, doesn't mean that somebody won't come up with alternative theories for this level of dark mass concentration. So this is the best evidence to date that we have for the existence of supermassive black holes, not only at the center of our own galaxy, but in fact anywhere in the universe. Harking back to those active galactic nuclei, this actually provides the justification that for that modeling. Okay, so now what? Now there's a lot left to do. So I do know there are many different directions to go, And our project with stellar orbits has effectively opened up a new approach to studying studying black holes, both in terms of the physics of black holes and the astrophysics of black holes. So there's tremendous amount that we can do going forward. Okay, so from the physics perspective, what we really are interested in is can we use these orbits to understand what is the complete theory of gravity? We know from the beginning of this talk that Einstein's theory of gravity, which is the best that we've had, and he's had a good run of it, right? He's had 200 years or so. There's all sorts of evidence that, that this theory is fraying at the edges. Right? The existence of dark energy might be one thing that you might ask, is this working? Dark matter is another place, and the existence of black holes. All sort of drives us to, especially black holes, to really explore what is the complete theory of gravity. And these orbits are orbiting in a regime that has never been probed before. In other words, it's kind of fascinating, actually. There are 4 fundamental forces. Gravity is one. It's the one that's most intuitive to us because we experience it every day. And yet, it's the least of the tested of those 4 fundamental forces. And so these orbits are in a regime that that hasn't been tested before. And you can make a series of tests. You can look at, effectively what you're looking at is how the curvature of space-time. So near a black hole or near something that's strongly gravitating, you get this exchange between space and time. So most of us think of space, on the one hand, the 3 dimensions of space, and then time is completely, with time being an independent thing. But when you get near a black hole, those things start to couple, and near the event horizon, they completely flip, actually. And so what we're looking at with these tests of GR, or general relativity, first is how does the photon make it from the star, and how is it affected by this warping of space-time, this mixture of space and time, from the star to us. So that's test number 1. Test number 2 is looking at what's known as the precession of the periapse. How does the object itself move through space? And then ultimately, one can inquire about the spin of the black hole. So the next closest approach is 2018, which used to seem very far away, but now is next year. So we are very much 2018 or bust for the entree into the realm of relativistic orbital modeling and tests. So that's very exciting to the group. A second aspect, which looks at the astrophysical drivers, is how do black holes grow, and what role do they play in the formation and evolution of galaxies? And here the story had changed. The scientific framework has changed so much over the course of this experiment. In the beginning, when we first announced the result of the black hole at the center of the galaxy, people used to ask which came first, the galaxy or the black hole. It was kind of like the chicken or the egg. And of course, we had all sorts of explanations for why one would come first and the latter and the other. But today, actually, thanks to a lot of work that's been done here at the University of Michigan, it's very clear that supermassive black holes and other galaxies seem to be correlated to the mass of the central component of the galaxy. And that suggests that we've framed the question in the wrong way. It's not which one came first, but rather they seem to have formed together, and there seems to be some feedback mechanism that allows these 2 things to grow in lockstep. And our galaxy is the only place in which you can see this process in action. Okay. Now, as is the case often with technology, if you have new ways of looking at things, you get new surprises. So not only did we went in with a question that we've answered, but now we have new questions. And just to give you a little bit of a taste, and I would say every prediction that has been testable has been inconsistent with the observations. So this is, I also like to call this is like job security, or for a scientist, this is like a candy shop, you know. Okay, so there's general lore in my field that you should only show images and never a spectrum. But it turns out there's so much information in a spectrum, it would be a mistake not to show you at least one. Okay. And the predictions have to do with what kinds of stars that might, at least some of the predictions, what kind of stars should you see near a black hole? And I'm going to divide them into 2 camps, young stars and old stars. And you can make lots of bad jokes about this, like in LA, that's all you have, young or old. And you take a spectrum, and this is the brightness is a function of wavelength. And young stars have, in this regime, one strong dip that corresponds to a transition in the hydrogen atom. And then the old stars have dips that look different. So it basically gives you a mechanism for understanding whether or not a star is old or young. And by old, I mean 1 billion years old. And young, I mean 1 million years. And again, to give you context, like if you were to anthropomorphize these stars, that would be, the young stars are like the age, the time scale of the human gestation period. So these are babes in the scheme of things. So what are the prediction for these things? The old stars have had a lot of time to interact with their surrounding, and there are all sorts of processes, gravitational interactions, that should induce these stars to settle down to the center of the system. The more massive ones going first, which means that there should be an entourage of old stars around the black hole. Okay, so the prediction is there should be lots of old stars around the black hole. The young stars form from big balls of gas and dust, where what you need to get these baby stars to form is gravity, self-gravity, to overcome any other force that might oppose it. Sort of like the same theory, or the same message of black holes. You need gravity to win, to get star formation to start. Now, these are two babes that I'm particularly fond of. They're a little older these days, and I would not want them near a black hole, because what is the problem? Well, near a black hole, how many of you seen the movie Interstellar? Okay, Interstellar made great. Do you remember the giant tidal wave in the movie? That was induced by the black hole. And that was induced because in a strong gravitational field, if say you sent someone you didn't like very well into the black hole, and they went feet first, the gravity would be pulling much more strongly on their feet than on their head. So that's called, that would be tidally stretched. Sometimes it's called spaghettification for obvious reason. But that's the exact opposite physical process that you need to get star formation to happen. Okay, so the prediction is you should not have young stars near the black hole. And in fact, that was the reason that was given for why we shouldn't get telescope time in the beginning. Not, the 3 reasons. The third was there are young stars kind of in this region, but far away. A black hole would be inconsistent with that. Okay, what have we seen? Okay, so this is our orbits once again, but now we're looking at an animation of the data that has been encoded with a tremendous amount of information. This is a collaboration with the University of Illinois to produce this nice graphic. And we're looking inside at the orbits that prove that there was a black hole, and we pull out, and there's color coding here. So the old stars, remember there should be lots, are orange. They're not there. There are very few there. So there's actually a dearth of the thing that we said should be abundant. The blue-green things are the young stars. Those are the things that we said shouldn't be there. They're the most populous thing that exists. And then the magenta things are the things we didn't think to make predictions about. So those were the unknown unknowns, and often, as is the case, those are sometimes the most interesting things that are there. So we have all sorts of ideas about what's happening here, but I want to emphasize that in spite of this wonderful technology that allows us to see these stars, we are only seeing the tip of the iceberg. These are these are the brightest stars that exist at the center of the galaxy. And if we know we think that they have any relationship to what happens in the outer parts of the galaxy, we know that the majority of stars aren't detectable yet. And that's because our ability to get high-resolution images is at the forefront, but basically clips us off. We're what's known as source confused. Sometimes how I feel, source confused, tracking all these objects. So a typical star, like the sun, is not detectable in our data. So you always have to be careful with your theories when you're only seeing the brightest. You might be seeing the exotica. It would be like trying to understand the stock market by only watching the largest transaction. You would be missing a lot of the picture. Now, maybe in the last minute or two, let me just look at, so we have all sorts of ideas. The theorists have gone crazy. in terms of coming up with new ideas, which is really when it gets fun from my perspective in science. Let me share with you one new idea that maybe connects our work to the LIGO experiment, the gravitational wave experiment. So those weird magenta stars are objects where we see the object being torn apart. This is the first time. We think this process happens in our models all the time, but it's actually the first time that it's been seen. The prediction, actually, when it was first proposed, was that it would be completely disrupted when it came through closest approach, but that didn't happen, which of course has sent us back into to the drawing board, actually. But people were really excited because, of course, at closest approach, with lots of gas comes off the top parts of the star, you have an opportunity maybe to feed the black hole. Because remember, our black hole is kind of on a diet. It's just snacking. And in fact, with these observations, we've seen it in snacking. You see that little red thing blipping up and down? That is actually the black hole feeding. So we're watching the dining habits. And the hope, actually, with this kind of observation was as it came through closest approach, you could see it, go through a feast. So again, this is just one fun connection that we've been able to make. Turns out people who study the stock market are really interested in knowing whether or not things change their state. So over the past few years, we got really excited. That thing is varying all the time. So while people were really excited about something happening, you had to be able to distinguish between what was already variable from the new thing that was variable. And the financial analysts know how to do this well. So we had a good time collaborating with a guy in the UCLA Business School to develop their techniques for astronomical purposes. And we can now very statistically soundly say nothing happened. So it was fun, but maybe not from an astrophysical perspective. Okay, so what happened? We actually think that what happened was not a gas cloud, but rather that two stars got very close to another, and the black hole has the impact of driving these two stars to merge. So I'd be happy to talk to people about this further, but this is a three-body gravitational interaction, and it solves so many of our problems. And it may make a connection to the unusual things that the gravitational wave experiment is experiencing. So let me not say too much more because I know we're running out of time here, except to say that in order to figure this all out, we really want to push forward with the technology. All of this, that's the best way forward. So today we use these one laser per telescope. We want to add to this 3 to multiple lasers because this allows us to more fully correct for the atmosphere. And if people are interested, I'd be happy to explain why. But that's essential if you want to get to the next generation of telescopes. The larger your telescope, the more limited only one laser will perform. And in the world, there are 3 next generation telescopes. There's the 30-meter telescope, which is a collaboration that the University of California is involved in. There's the Giant Magellan telescope, which is a collaboration that the University of Michigan has some participation in. And then there's the European Extremely Large Telescope. There's all sorts of amazing technical challenges associated with this observatory, one of which is that it will be the largest moving structure ever built on this planet. So people who build astrodomes are the people who will build these facilities. Because you do not want weather in your telescope. Okay. So the center of the galaxy should look quite a bit different. So this is where we think we are roughly today. This is a slightly old animation. And then going further, you should be able to see that zoo of the ordinary stars buzzing around. So I think there's an exciting future here, both in terms of the physics and astrophysics of black holes. And of course, this work has been done in collaboration with a great number of people over a very long time scale, and I've had the privilege of having some pretty amazing students in the group. So thank you for your attention, and I'm happy to take questions.
All right, we have time for some questions. Who would like to go first?
So besides the clearing up the atmosphere with distortion, does the atmosphere limit you in terms of like the infrared you can pick up? that you need to get out of the atmosphere to see certain infrared?
So the atmosphere is much better, the atmosphere presents two challenges. One is it absorbs, and two, it distorts. So there are whole bands of wavelengths that are just completely absorbed by the atmosphere. The infrared is an interesting band because there are pockets that get through pretty effectively, and then there are pockets that you just need to go to space. And so you can go high up. That's one solution. In fact, another solution is to telescopes that are on board planes. So the Sophia Observatory is a 747 with a hole cut out of it, and the telescope rides aboard. So they get up to about 40,000 feet. And then, of course, you can just put it into space. And basically, from the ground, you can effectively observe in the optical, some bands in the infrared, and the radio, and then pretty much most other things you're going to space for.
Presumably, the black hole is at least attracting, if not gobbling up, dark matter as well as ordinary matter. Is there anything you can learn about the distribution of dark matter or anything else by looking at what you can see around the planet?
Yeah, actually there's two ways. I mean, so one thing is that these orbits, the presence of dark matter should imprint on the orbit. It's like at the precession of the periapse. So in fact, actually, let me say a little bit more about that. So the curvature of space-time, instead of these orbits coming back to where they came to, gravity will have the orbits will overshoot. So you'll get like a kid's spirograph pattern. These extended matter will actually do the opposite thing. So you'll have these orbits open up. So the orbits themselves are an important probe of what's at the center of the galaxy. And the question then becomes, what dominates? Is it going to be stellar remnants? So in other words, the ordinary mass black holes and other things like neutron stars or white dwarfs? Or will it be dark matter? So it's sort of a messy detection of dark matter. A second thing that I'm increasingly interested in, and we had a nice chat today, this afternoon, is the idea that that dark matter is expected to be peaked, just like the old stars. So the old star, so we said it should congregate, but for other reasons, or the dark matter should be sharply concentrated at the center of the galaxy. And one might anticipate that these stars that are orbiting through this goop of dark matter should be affected. So you could imagine dark matter-powered stars. So one of the questions that we have is, actually I didn't really emphasize this, but in this animation, you hopefully notice that the young stars form in a disk. So as you pull back, there was actually a preferred plane. But inside that organization, there's a very disordered set of young stars. And those young stars kind of look different than the others. So maybe something else is going on, and that's the region in which the dark matter should be particularly well concentrated. So it's interesting to ask, is the unusual characteristics of those stars a signature of dark matter? We don't know. I mean, it's just yet one more of these ideas that have been put out there to explain the unexpected population that we see around a black hole.
The young stars that you're seeing, where do they come from? Where did they were born in?
Yeah, good question. I have no idea.
Could have been eaten up by the black hole?
Yeah, it could have been. So, I mean, there were all sorts of ideas. So when these stars were first found, I'd say they were in three classes. One is they're not young. They're just young, old stars masquerading as youth. So something's changed them. So the dark matter infusion idea for the ones in the center doesn't work quite as well at the larger radii, but maybe you stripped them somehow or did something. So that was one idea. Another class of observation or suggestions was maybe you form them really far away and where the tidal forces aren't so bad, and you put them on an express bus, something, that brings them in really quickly. The question is, what does that migration so quickly? People could invoke things like intermediate mass black holes, an interesting idea, never been seen. So again, you're sort of, you're looking for an explanation and you're grabbing at something that is equally controversial. And then that last set of suggestions was that they really are young and they really did form there. And so what happened to the gas? You need gas densities that are at least 10 million times higher than what we see today. So the usual way out is you say, well, maybe there was an infalling cloud of dust, of gas, that formed a disk around the black hole, and from that, these stars formed. It also suggests that that gas, because that process is not very efficient, that there was a lot of gas around the black hole at that time, and that might have fed the black hole. So in other words, there's an associated suggestion with this, that the black hole was much more active in the past. In other words, it looked like an active galactic nuclei at the time that these stars were being born. Now, the fact that there is a plane, an orbital plane associated with these young stars is a hint that that's probably an interesting direction, because you see a preferred plane. So that is the most popular idea today.
In active galactic nuclei that we look at, is there enough material there to form this many stars?
Yes. So you could imagine that this phenomenon is actually ongoing in places that we just can't see this level of detail. Yeah.
So in our search for never evolving technology, I was just handed a microphone. I am dying for someone in the middle to ask a question, because you know what this microphone is for? All right, you ready?
That's awesome.
Here you go.
How does the preferred plane you described here align with the plane of the general plane of the galaxy?
It doesn't. It doesn't line up with anything. And so at first you might think, oh, that bothers me. And then you might think, maybe it's not that big a deal. Because you need 10 to the, roughly, I think 10 to the 4 times the mass of the sun worth of gas. So maybe it was just the last cloud that fell in. So maybe it's okay.
Okay. I was just wondering does the formation of a galaxy, is it similar to how a star is formed, like how a dense cloud is collapsing within itself and in turn will create an ellipse of some sort and then will somehow attract a disk around it? Is that how inevitably the galaxy is formed?
So yes, the short answer is yes. And it's because the physical processes that control star formation and galaxy formation are very similar. So the two key components are gravity. You start with something that's a big cloud of something that collapses. But both clouds are rotating. And so you have the conservation of angular momentum problem, which is, well, I don't know if it's a problem, but it's like the spinning ice skater who starts spinning slowly with their hands outstretched and brings them in and spins faster. And because of that, what happens is that it's easier for things to collapse along the direction that they're spinning. And it's harder to collapse this way, because ultimately if you collapse in too close, you start to rotate faster than the speed of light, which you're not allowed to do. So it's the solution to that physically is that some mass is left at large radii, perpendicular to the spin axis. So that's why you get flattened pancake structure. So you start with something that's big and spherical, rotating a little, and it's easier for it to collapse this way. So you get a lot of flattened pancakes.
So there's like a very high metallicity within the center of the galaxy?
Oh, well, the metallicity, that's a slightly different question. And of
There's
course,
a lot of older stars, right?
yeah, and then for the rest of the audience, metallicity from an astrophysicist perspective is most of the universe was hydrogen, then you get some helium, and then we call everything else metals, which chemists would just shrink at. But it's a few percent. So most of the universe is hydrogen. So things become more enriched by stars forming and exploding. So if you look, the insides of stars can process things all the way up to iron, and that's it. And if you think about the chemical complexity of life on this planet, we're way beyond iron. And all of that is produced in supernova. So that explosion that happens in 1 second, that provides the energy that allows the chemistry to progress beyond iron. So there's a lot to be learned from the universe.
Oh, I so much want to throw this to you. But I think friends.
Sorry for a second question. Has anybody looked at how much mass would have to fall into that black hole to create a radiation danger that we need to be concerned about 35,000 light years away?
Oh, I should have said, yeah, we are safe.
You should tell us.
Yeah, okay, we are, the black hole, black holes have very bad reputations, right? And also all sorts of misconceptions. The most frequent one is that they're cosmic vacuum cleaners, which is not correct. You have to be incredibly close to the black hole in order for the black hole to tear a star apart and fall in. In other words, those stars, these are much closer than the sun. These stars are going to happily orbit for their entire lifetime. So out here in the galactic suburbs, we're fine. There's no danger presented to us by the black hole. No.
You still have to pay your taxes.
All right, are there any further questions? Preferably in the center of the... Hey, no, Fred. Okay. Are you ready?
How do you detect if a black hole is rotating? And if it is rotating, how does that change its gravitational effects?
Okay, so the spin of a black hole is going to affect the gravitational field. So anything that can probe the gravitational field very precisely may tell you whether or not there's the black hole is spinning. So one way has been to look at the shape of high energy lines in the X-ray. So the shape has been interpreted as gas rotating very near the black hole. So the shape of that profile, there's asymmetries which have been interpreted as the spin of the black hole. Similarly, these stars are sufficiently close. So in principle, if you keep going with this, you'll see the imprint of the spin. You just need to keep going. So I like to say, like, this project is like a fine wine. It just gets better with time, and then technology gives it an enormous boost.
All right, it's getting a little bit late. Let's thank Professor Ghez for a wonderful talk.